These are the third notes about acids and bases. Let me recap some of the things we have learned about acids and bases really quickly. Today we will get quantitative. Now, I know this looks bad, but by the end of these notes, you will understand how to use these equations. Right now, most likely it looks like a bunch of gibberish to you, like another language or some strange formula, but actually you're going to find that these are the ways we get quantitative with acids. These equations are not as bad as they look. I would even argue that at least two of these equations are easier than addition. I'm going to make that statement. These are easier than adding, one of the easiest things to do in all of mathematics. People are often intimidated by it, but super simple, as you will see, I hope. Remember that acids and bases are usually in the form of a solution. So all the things that we learned about solutions apply. A mixture of two chemicals that is stable and homogeneous. The solute is less, the solvent is more. Well, what's the universal solvent? Water. So most acids and bases are aqueous solutions with water. So that means the acid or the base would be the solute, right? And then we talked about measuring concentration. Well, in this section, we're going to forget about molality. We're going to forget about parts per million. We should have forgotten about that to begin with. And we're going to only have one left, and that is molarity. Molarity is the only one we use in acid-base chemistry. So you got to remember what molarity means. Moles of solute over liters of solution. That is the default measurement for concentration in chemistry. We talked about one definition, the Arrhenius definition, that an acid generates hydronium in solution, probably aqueous solution. A base generates hydroxide in solution, probably an aqueous solution. Those are the definitions of acids and bases. Those are the ones that we use all the time. Based on these definitions, water can fall into either category. Water is an acid, or water is a base. What's the word for that? Like an amphibian, amphoteric. Amphoteric chemicals can act as acids or bases depending on their surroundings. So water can never be pure. This is the dirty little secret for water. Water can never be pure because even if you tried to get every other chemical away from it, purifying it as much as you possibly could, this happens. Water ionizes itself. It does it to itself. Nothing else needs to be present. You get a very small amount of hydronium and hydroxide present in the purest water possible. So notice how they form. Hydronium and hydroxide form together. They form at the same time. That means for every single hydronium you make in pure water, you will also have a hydroxide in pure water. So their numbers will be the same, and their concentrations will be the same. This is important for understanding pH. Oh yeah, there's that other definition, the Bronsted-Lowry definition of an acid or a base. Whether it is a proton donor, that's an acid, or a proton acceptor, that's a base. Those are very polite terms, but as I said, a proton donor doesn't just give away its proton or hydrogen ion. It is ripped away. It's taken away from it. And then a base doesn't just accept it in the mail like sign for a package that's delivered. It actually goes and grabs that proton. So this is the other definition of an acid and a base that we're going to be using. And then we talked about a few other things like acid strength depends on dissociation. And then we also mentioned that some acids are monoprotic, some acids are diprotic. That will come up a little bit later. So now, the new stuff. pH. Everybody has heard of pH. pH is a scale that we use in chemistry to measure something. What are we measuring? We are measuring the power of positive hydrogen. I've added that to quote the Lou Reed song, but what pH really stands for, you might not have realized that it's an acronym. It stands for the power of hydrogen, pH, power of hydrogen. And what we mean by power is we mean exponent, like to the power of 2, to the power of 3, to the exponent. Okay, so in chemistry, if you put something into brackets, like you see the H plus right there, that means the concentration of that chemical. So brackets indicate concentration. This is something you may have noticed. I've shown it a few times so far, but now we're going to really need to use this quite a bit. So I'm going to point it out very clearly that if you throw a chemical into those squared off brackets, they're not parentheses, which are round, they are squared off brackets, the chemical inside, that means the concentration of it. And of course, that's going to be in molarity, because molarity is the default in chemistry. Okay, so in pure water, hydronium and hydroxide have the same concentration. We just mentioned why. Because for every hydronium that forms, a hydroxide also forms. Well, if you were going to try to guess how much that would be, good luck. That would be an incredibly difficult calculation to figure out how much hydronium or hydroxide would form in pure water. It depends on so many collisions, thermodynamics, the size of the molecules, the polarity, all the angles, everything. So let's not do that. Instead, what we've done is we've gone out and we've measured it. I wonder how much there is in pure water. And they've measured pure water again and again and again and again. And what they find is that as long as you're close to room temperature, on here it says 25 degrees Celsius, but it doesn't make much difference if you're a little bit above or below that, anywhere near normal temperatures, you will find that the concentration of hydronium and hydroxide is 1.00 times 10 to the minus 7 molarity, capital M. And that goes for both of them because they have to be the same. Now look at that, -7. Is that a big number? No, if it's 10 to the -7, remember, that is a very small amount. That means it is 0.0000001 molarity, a very, very vanishingly small amount. So when I say water can never be pure, well, it can be pretty pure. It can be 99.999, but it can never be completely pure. So that concentration is going to be pivotal because the concentration of hydronium and hydroxide in pure water is what the pH scale is based on. The concentration of hydrogen ions is critical in many chemical reactions. It determines whether all kinds of things will happen, like if a base will be neutralized, if a base will react, if a metal will react, and so on and so on. Lots and lots of things depend on it, so we like to keep track of it. So the pH scale is very much like the Richter scale that measures earthquakes. And both of those scales are what we call logarithmic. Now, a logarithm is a fancy mathematical word, and people think that it's, ooh, intimidating, that must be hard, sounds hard. It's not hard. It's one of the easiest things to do in mathematics. I will say even easier than addition. I will show you how to do it. So the definition of pH is the negative logarithm of the concentration of hydrogen ions. See those brackets around the H plus? That is the concentration of hydrogen ions. So that sounds bad, but it's actually fairly easy. Also, you can say that the concentration of hydrogen ions is equal to 10 to the negative pH power. And I'll show you that one too. That is also much easier than it sounds. So a logarithmic scale is a scale that changes dramatically. With every change of 1, it's a huge change. Like, for example, if you experience an earthquake and it's a magnitude 3 and you feel the shaking, And then you hear in the news about a magnitude 4 earthquake that happened in another part of California, and you think, oh, well, that's just a little bit more. 4 is just a little bit more than 3, right? No, a magnitude 4 earthquake has 10 times as much shaking as a magnitude 3. And if you heard about a magnitude 5 earthquake happening in Indonesia, you think, oh, that's just a little bit more. But no, a magnitude 5 is 100 times stronger in terms of shaking than the magnitude 3 earthquake. It's a logarithmic scale. So every change of 1 is a really big change. So we're dealing with negative logarithms. So it turns out that the lower pHs are higher concentrations. I'll show you this more later. This may not make sense yet, but it will later. So a lower pH like pH 1 or pH 2 is a higher concentration than like pH 9 or pH 10. Those are actually lower concentrations. So it's a little bit of an upside down scale. That's one thing to remember. And pH 2 is equal to 0.01 molarity. pH 4 is equal to 0.0001 molarity. So the pH scale condenses any possible value of hydrogen ion concentration to a 14-point scale. And the reason it can do this is because of the definition of molarity, because you can only use molarity while you have the same solute. If the solute becomes the majority, well, then suddenly it's the solvent. So it reduces the whole scale to a 14-point scale. You can only go from 0, there is a 0, to 14. So notice the way that I'm writing it here, it looks a little different. It says the pH is equal to the negative logarithm, but I'm not writing hydrogen ions, I'm writing hydronium ions, the concentration of hydronium ions. Now, why is that? Because hydrogen ions in a solution, in an aqueous solution, are immediately going to make hydronium. So they're the same thing. As long as you have an aqueous solution, the concentration of hydrogen ions is exactly identical to the concentration of hydronium ions. So I prefer to write it this way to talk about what's really going on. Okay, so they could have called it the pH 3O scale actually, but they just called it the pH scale. Okay, they could have also said the concentration of protons. Again, that's the same thing. So just you have to be able to recognize that when we talk about the concentration of H+, put an H+ in brackets, that is the same thing as putting an H3O+ in brackets, or even, we don't usually do this, but putting protons, like a P+ in brackets. Okay. And then at the bottom, I'm writing the concentration of hydronium ions is equal to 1.0 times 10 to the negative pH. So what that means is if you take the pH number and put a negative sign in front of it and throw it up as your exponent, well, that'll give you the concentration, 1.0 times 10 to that. Now, a lot of people are very intimidated by logarithms, but logarithms are super, super simple. If you understand what they mean, they become super, super easy to do. You don't even need a calculator to do them, as long as it's a multiple of 10. If you're doing a logarithm on anything that is a multiple of 10, logarithms can be done in your head without a calculator very easily. So we're going to take the logarithm of 1,000. Right now I'm not using units. Logarithms do weird things to the units. Sometimes we leave the units out when we're doing logarithms. We'll talk about that later. But for now I'm just talking strictly mathematically. What would this is a base 10 logarithm, by the way, for math nerds. What would the logarithm be of the number 1,000? Well, the best way to do this is to rewrite the number 1,000 in exponential form, in scientific notation. Well, 1,000 is 10 to what power? How many zeros are there? Oh yeah, there's 3 zeros, so it is 10 to the third power. Now that I've written it this way, you can find the logarithm by simply doing this. What is the logarithm of 1,000? What is the logarithm of 10 to the third? It is 3. So notice what I did there. I didn't change the number. I didn't do anything to the number. I didn't add or subtract. I just took the number down from the exponent, and that was my answer. That's what I mean, that taking the logarithm is easier than addition. It doesn't even change that exponent. So because of the way logarithms are defined, as long as you put 10 to a power, that power is your logarithm. Isn't that easy? Much easier than you probably expected. Let's do another one. Ooh, this one's much bigger, right? So what number is that? Well, there's 1,000, million, billion, right? This is 1 billion. What is the logarithm of 1 billion? Well, probably want to write that in scientific notation, or at least 10 to a power. So how many zeros do you see there? 9. So that means it's the same thing as 10 to the 9th. Now I could write 1 times 10 to the 9th, but for simplicity, I'm just writing 10 to the 9th. And what's the logarithm of a billion? What's the logarithm of 10 to the 9th? You know. Right. It is the number 9. So the logarithm of 10 to the 9th is 9. You just take down the exponent. It really is that easy. As long as you can put it into that form, you just take down the exponent. Sometimes it is given in that form, making it even easier. Ooh, this one looks different. This one is a small number. It's less than 1. The log of what number is that? That's not 1/10, that is 1/100th, right? So what is a logarithm of 1/100th? Well, 1/100th is 1 divided by 100, and that means that the 100 is in the denominator, and that means that the exponent would be negative, of course, and 100 has 2 zeros, so that's the same thing as 10 to the negative 2. The other way to figure that out is, well, you would just move the decimal 2 places to the right. That's the wrong way to move it, so your number is going to be negative. To get behind the 1, you have to move it 2 places to the right, so you get a negative exponent. So as long as you can put the number in 10 to a power form, if you can put it in this form, in scientific notation form, then the logarithm is very obvious. What do you think the logarithm of 10 to the minus 2 is? It is minus 2, negative 2. So remember, the negative comes along with it. So this becomes a problem because people don't like negative numbers. People are confused by negative numbers. And a lot of the concentrations we're going to be using are going to be a form sort of like this with a negative exponent. So they figured out a way to get rid of that negative number. By the way, if you have 1 times 10 to the minus 8, what does that equal? 0.0000001. That is 7 zeros after the decimal. So remember, negative 8 means that you would have to move the decimal 8 places to the right to get behind the 1. Don't forget the position of the 1 itself. Okay, that's a very small number. So 10 to the negative 8 is much, much smaller than 10 to the negative 2, isn't it? So the bigger the negative exponent is, the larger the value, I should say, of the negative exponent, then the smaller the total number is. So what would be the log of 10 to the minus 8? Well, the log of 1 times 10 to the minus 8, which is the same as 10 to the minus 8, you know what it is. It would be negative 8, right? But look at this. I'm not taking the log of it anymore. Notice the difference? I'm taking the negative logarithm. So what difference do you think that makes? Taking a negative logarithm is the same thing as taking a logarithm. The only difference is, whatever your answer is, you flip the sign. So if your answer is negative, you make it positive. If your answer is positive, you make it negative. So since our answer would have been negative, and it's a negative logarithm, what is the negative logarithm of 1 times 10 to the minus 8? It's just 8. So the reason they did this on the pH scale, the reason they decided to use negative logarithms, is because they didn't want to have negative pHs. They only wanted to have positive pHs. Because again, positive numbers are just easier for the human mind to deal with. So just remember that every pH will be a positive number because of the way it was defined. Don't get confused by that. All pHs are positive. It only goes down to 0. That is the limit. It stops at 0. It doesn't go negative. So 1 times 10 to the minus 8 is equal to 0.00000001. That's a very small number. 5 times 10 to the minus 8, oh, that would be the same number of zeros. I won't repeat them, but with a 5 after it. So is that a larger number or a smaller number? The 5 times 10 to the minus 8, of course, is a larger number than the 1 times 10 to the minus 8. So notice what I'm doing here. I had a 1 there, and now it's a 5. Let's see, later, if I added more, it would be 6, 7, 8, 9, and then eventually it would go to 10. Well, wouldn't that flip to the next digit over, to the 1 to the left? And that position would be 10 to the minus 7. So notice that we're actually heading toward 10 to the minus 7, if you think about it. So if you ever have to take a logarithm of a number that doesn't start with 1 times 10 to a power or just 10 to a power on its own, well, those are much harder. Those are harder than I've advertised. But all I want you to realize is what they're in between. Is it moving up or is it moving down? So remember that we said the negative logarithm of 1 times 10 to the minus 8 is going to be 8. So what about 5 times 10 to the minus 8? Would the negative logarithm of 5 times 10 to the minus 8 be greater than or less than 8? So remember what I said, we were moving towards the minus 7. And if it was 1 times 10 to the minus 7, the logarithm would be 7. So is 7 greater than or less than 8? 7 is less than 8. So remember, if you have any other number other than 1, any other number other than 1 in that position, so let's say 2 times 10 to the minus 8, 3, 4, even if it's 1.1, whatever it is, it's going to be less than the equivalent pH if it had been 1. So the good thing is it's always that, so you know whatever the number is there, you can put a less than sign. And that's all I expect you to be able to do, because yes, logarithms become much harder if it's not a multiple of 10. If it's not 1 times 10 to a power, then they do become harder. But the ones I'm expecting you to do are the ones that are 1 times 10 to a power, which are as easy as I've advertised, easier than addition. This is the way that many people are familiar with pH. They're familiar with the universal indicator scale with all those pretty colors, kind of like a spectrum of colors, a rainbow of colors. And on the universal indicator scale, acids show up as red or orange, bases show up as purple or blue, and if you're neutral, you're going to be on the green. Notice that the pH numbers go from 0 to 14, and 7 is in the middle of that. 7 is neutral. If you're a lower number than 7, okay, then it's an acid. And if you're a higher number than 7, it's a base. The farther you are away from 7, the more concentrated the acid or the base will be. So pretty much it's kind of safe in the middle, hazardous on the sides. Now we're going to see mathematically where these numbers derive from, because these numbers are actually negative logarithms. So now you're going to see where they originate. Just remember that negative logarithms produces an upside down scale. So the concentration of hydrogen ions, pH, power of hydrogen, the concentration of hydrogen ions is highest where the number is low, like 0, 1, 2. That's where there's the most hydrogen ions. And the concentration is the lowest where the number is high, 12, 13, 14. Those are the lowest concentrations of hydronium or hydrogen ions. There is a relationship between hydronium and hydroxide. They are only ever equivalent in a neutral solution, which is right at pH 7. That would be like distilled water, for example. In an acidic solution, well, of course, acids generate hydronium, So you would expect there to be more hydronium in an acid than there would be in distilled water, of course, but what you might not expect is that there would actually be less hydroxide. In an acidic solution, there is always less hydroxide than there had been in a neutral solution. So why is this? Well, imagine if you're introducing an acid into a solution, you're stirring it in, what's it doing? Well, you could think of it two ways. It's generating hydronium or it's donating protons, right? Well, those protons, the reason it generates hydronium is because it's donating protons, and those protons are sticking to water. But aren't some of them going to stick to the hydroxide that's in that solution? There's a little tiny bit of hydroxide. And if they do, if you add a H plus to an OH minus, doesn't that make H2O again? So what acids do, when you put them into solution, another thing they do, which isn't listed in the definition, is they destroy hydroxide. They basically repair it, turn it back into water. It's kind of the opposite thing for a base. It might be a little harder to visualize this, but if you're adding hydroxide, if you're generating hydroxide in solution, well, some of those hydroxides are going to grab a hydrogen ion from a hydronium. They're going to eventually just run into them and grab them, and they're going to be restored into water as well. Okay, so it's going to convert some of the hydronium back into water as well. So that's why there's less hydronium in any base, any alkaline solution or basic solution, than there is even in distilled water. So notice that's like a teeter-totter. So on the left side, the acids, you've got a concentration, you've got more hydronium than hydroxide. In the middle, where you have a neutral solution, they are balanced, exactly the same number of hydronium and hydroxide. And on the right side, where it's a basic solution, you've got way more hydroxide and less hydronium. This is the relationship between hydronium and hydroxide. So what kind of relationship is that when one quantity goes up and the other goes down? When one increases while the other decreases? Oh yeah, that is an inverse relationship, I should say. They are inversely related. Now, the teeter-totter metaphor here might reverse what I'm saying. When I say it goes up, what I mean is it increases, but on the teeter-totter, the one that gets bigger pushes it down. So the metaphor doesn't work ideally here, but remember, it's an inverse relationship. They're doing the opposite of each other quantitatively. So because of their inverse relationship, there is a way to calculate one from the other. There is a way to calculate the hydronium from the hydroxide or the hydroxide from the hydronium. And this is called the equilibrium constant of water. It turns out, because they are inversely related, the product of the two of them is always the same number. This is called the equilibrium constant for water. An equilibrium constant expression relates the concentrations of species involved in an equilibrium. So the word species here, this is the chemistry definition of species, not the biology one, kingdom, phylum, class, order, family, genus, species, the classification, the Linnaean classification of life. A species would, in that case, would be a specific kind of living thing on the earth, okay? But in chemistry, a species is a sort of chemical, a kind of chemical. Like an acid is a species, or a base is a species, a salt is a species, an indicator is a species, etc., etc. Okay, so the relationship for the water equilibrium is, in the middle here, the concentration of hydronium multiplied by the concentration of hydroxide equals Kw. The equilibrium constant, called the self-ionization constant, is so important that it got its own special symbol, Kw. Kw is the one for water, and that is the one we're going to be using in this unit. So the great thing about the equilibrium constant for water is that we can actually derive it. We can figure out what it is. We don't have to do measurements to find it. Well, we've done measurements to find the concentration of hydronium and hydroxide, right? But we can use those to calculate Kw. So once you see how Kw is derived, you can always reconstruct it if you need it. So the value of Kw can be found from the known concentrations of hydronium and hydroxide in pure water. Remember, hydronium and hydroxide in pure water have the same concentrations, and both of them are 1.00 times 10 to the minus 7. So one thing I want to note here is you may have noticed when I was showing you my logarithm examples, I wasn't putting units. And that's because, well, maybe I'm being a little sloppy, but logarithms do weird things to units. It kind of destroys a unit in a funny way. So a lot of times when we're taking the logarithm of something, we might occasionally just leave out the unit and just remember what it is. But remember, all of these concentrations are given in molarity. So please forgive me if I leave out a unit like I have here and didn't write in the capital M. Sometimes I will put the unit in there, but the problem is when you wind up taking logarithms of things, they get destroyed, and then there's another reason as well that you'll see shortly. So if Kw is equal to the concentration of hydronium times the concentration of hydroxide, and if those are the same number, 1.00 times 10 to the minus 7 molarity for each, well then it's really like squaring it. 1.00 times 10 to the minus 7 multiplied by 1.00 times 10 to the minus 7. Well, that's easy, right? That's easy. 1.00 times 1.00 is 1.00, right? And 10 to the minus 7 times 10 to the minus 7. Oh yeah, what do you do with those exponents again when you're multiplying? Oh yeah, it's like adding. So what's negative 7 plus negative 7? Well, they're both negative numbers, so if you add them, the answer is going to still be negative, and it's negative 14. Boom. That is the value of Kw. 1.00 times 10 to the minus 14. What about a unit, you ask? Well, this is the tricky part. If you had molarity for each one of those, then the unit would kind of be molarity squared, or moles squared per liter squared, but not quite, because actually, well, it was moles of one chemical and moles of a different chemical. Ooh, this is getting really, really ugly. So in fact, if you were to write a kind of a unit for Kw, it would be about the ugliest unit that ever existed. So guess what we do? We just leave it out. So Kw is usually written without a unit. Just remember, if you use Kw to solve for a concentration of any chemical, your answer will come out in molarity. Molarity, capital M, for sure. And this would have worked at any other concentration of hydronium and hydroxide. Just the trouble is we don't always know them at other concentrations. Like for example, if they're not the same, then you have to figure out what each one is. So this was the simplest location to calculate Kw, but Kw stays the same at whatever the concentration of hydronium and whatever the concentration of hydroxide may be. I'll show you a little later how to use this to calculate one from the other. If you know the concentration of one of those two, you can always use it to calculate the other one. Okay, if one increases, the other decreases. It's an inverse relationship. We'll be doing that a little bit later. So when we're talking about the pH scale, and you remember it goes from 0 to 14, some pHs have very, very concentrated acid, like pH 0. That would be like the acid in a battery. Think of a battery in your car. Very concentrated acids because they're very good electrolytes. They're the best electrolytes. But then you have acid even in your stomach, about pH 2. Now, our bodies can contain acid, interestingly, because acids don't normally react strongly with organic materials. What they react more with are metals and bases. A lot of people think, oh yeah, acids are dangerous, word on the street is out, acids are dangerous, you don't want to go near them. And then if they're opposites, well then bases must be safe. But no way. Bases are equally dangerous. In some ways, you could argue that a base is more dangerous to a living thing like us, to a living creature, because they do tend to react with organic materials. For example, look on the other side, pH 14. Well, that has very, very little hydronium in it, vanishingly little hydronium, and it has a whole lot of hydroxide if you're way over there, like drain cleaner. Well, why do we use drain cleaner to clean out a drain? Well, think about it. This might be kind of gross, but things that go down the drain are organic things like hair, for example, organic materials. That's what usually clogs the drain. So if you want to clean out your drain, you want to pour down something that reacts with organic materials, and that would be a strong base. If you pour an acid down your drain, I would not recommend it because acids react with metals. A lot of drain pipes are metals. So if you pour acid down the drain, it doesn't necessarily clear out the clog, it actually destroys the pipe itself. So we try to avoid pouring concentrated acids down through the plumbing, okay? And then if you're near the middle, like pH 7, well, of course, that's pure water, but there's actually many solutions that can have a pH of 7. As long as what it contains is not an acid or a base, it can remain at pH 7. And then many cleaning products are mild bases, like notice where soap is located, okay, around pH like between 9 and 10 sometimes. Soaps are alkaline, and things we consume, a lot of things we consume are a little bit on the acidic side, but they're not too far off, like coffee and juice. Okay, lemon juice can be pushing it. That's why we can have a reaction to it. But generally, the things we consume, the things that we put into our bodies are going to be closer to the middle of the range. Remember, this is a logarithmic scale, excuse me. So every change of 1 is a big, big change. So as long as you stay away from the two ends, you're more likely not to run into serious trouble. There are ways that neutral solutions can be hazardous. I'm not saying that they're all safe, but you should always be wary if your pH is very, very low, like pH 0, 1, 2, or very, very high, like 12, 13, 14. Those are the hazard zones. So many people have a passing familiarity with the pH scale, which goes from 0 to 14, not 1 to 14, 0 to 14, and measures the concentration of hydronium. But now you should be able to understand what it means quantitatively. You can use that scale as a handy way of figuring out the concentration of hydronium. So for example, if it's pH 3, well, the concentration of hydronium is just going to be 1 times 10 to the negative pH. So if it's pH 3, it'll be 1 times 10 to the minus 3 molarity. If it's pH 7, it's 1 times 10 to the minus 7 molarity. If it's pH 11, it's 1 times 10 to the minus 11 molarity. So do you see how this scale really gives you the concentration of hydronium? That is your exponent if you just make it negative. But remember that a negative exponent can be misleading because let's say the more negative it gets, like negative 3, negative 4, 10 to the negative 3, 10 to the negative 4, the smaller the value of the number is getting. So don't forget that the pH scale is kind of upside down, if you want to think of it that way, where the highest concentration is at 0. The lowest concentration is at 14. So you just got to keep track of that. So remember that 0 and 1 are very concentrated acids. There's another scale that you might be less familiar with. In fact, I'm pretty sure you've never heard of it, and that scale is called the pOH scale. Well, guess what it does? It's based on the negative logarithm of the concentration of hydroxide, the pOH scale, right? And remember, hydroxide and hydronium, they have an inverse relationship. Don't forget that the pH scale is really measuring hydronium. You could think of them as hydrogen ions, but I think it might be better to think of them as hydronium. That's what they really are. So these two scales are going to be kind of like opposites. Well, if you use universal indicator to show your color, the colors will be the same, but the numbers will wind up being, guess what? The exact opposite. So what's the point of having a pOH scale? Well, I think if you know of its existence, it's really easy to remember what the numbers will be. They'll be the opposite of the pH scale. For example, whatever the pH is, you take 14 minus that. 14 minus the pH gives you the pOH. Notice how at any point, they really just add up to 14. So if you start at the beginning, 0 and 14, they add up to 14. Over here, a little bit further along, 3 and 11, they add up to 14. 9 and 5, they add up to 14. 12 and 2, they add up to 14. At any point on the pOH scale, it's going to be 14 minus the pH scale. So what's the point of using that? Well, actually, it can really quickly help you determine the concentration of hydroxide. So if you know what the pH is, you can almost instantly establish the concentration of hydroxide, which is like a shortcut. It'll save you some work. So just be aware of this, the existence of this scale. You actually never really have to use it. It's kind of a shortcut, and it helps you jump to the answer a little more quickly in some problems. So remember, the pOH scale is the exact reverse of the pH scale, and at any given point, they both add up to 14. Just like they multiply together, if you think about it, the concentrations multiply together to be 1 times 10 to the minus 14. So that's where that 14 comes from. So in review, remember that pH is defined as the negative logarithm of the concentration of hydrogen ions, or hydronium. So if the concentration is 1 times 10 to the minus 8, like in the first one here, 1 times 10 to the minus 8 molarity, capital M, well, you take the negative logarithm of that, and you get 8.0. The molarity, by the way, is kind of destroyed by the logarithm function, so that's why pH are not given a unit. They're one of the few things that you're going to find, other than unitless ratios, which are all over the place, that do not have a unit. pH does not have a unit. It's just pH 8.0. That's it. So what about in the second one? What's the pH? It's the negative logarithm of the concentration of hydrogen ions. If the concentration is 1 times 10 to the minus 7 molarity, well, obviously, you take down the exponent, and it's a negative logarithm, make it positive, and it's 7.0. So that is what I mean. That part is easier than adding, easier than addition. No problemo. So remember that that's what pH 7 means. It means you have a concentration of 1 times 10 to the minus 7 molarity of hydrogen ions. Looking down in the next box where we have pH 6, well, you can use that 6 to find the concentration if you just stick it up as your exponent. Oh yeah, but we have to make it negative. So remember that pHs are never negative. The lowest value they can have is down to 0, okay? But the concentrations are usually a negative exponent. 1 times 10 to the minus 6 molarity. So we took the pH 6, put a negative in front of it, and made that our exponent. So what if it was pH 2? What would the concentration of hydrogen ions be? 10 to the negative pH. So 1 times 10 to the negative 2 molarity. So don't forget that 1 times 10 to the minus 1 is equal to 1/10. And 1 times 10 to the minus 2 is equal to 1/100th, right? So what about 1 times 10 to the minus 5? Well, it might be harder to say what the name is, but think about how many zeros would you have after the decimal. If it's 1 times 10 to the minus 5, you would have 4, because don't forget, the 1 takes up one of those 5 positions. So imagine that you've moved the decimal over 5 places to the left. That's what that means. In other words, 1 times 10 to the minus 5 is a much smaller number than 1 times 10 to the minus 2. And 1 times 10 to the minus 2 is a smaller number than 1 times 10 to the minus 1. So that's why the pHs, like pH 1, have a higher concentration than pHs like pH 2 or pH 5, because think about what they mean. So I'm going to do a few pH calculation examples so you can see how these are done. So now we're getting quantitative. I wanted to give you some examples that you can base your problems on. We are now going to use these three equations. Hopefully now you understand what at least two of them mean. One of them I haven't given enough information about. I'll show you in the example. Okay, so the top one I'm going to call the Kw equation, and you can solve for one if you know the other, one ion if you know the other ion. The next one is a pH definition, negative logarithm of the concentration of hydronium. And the third one is the way you find the concentration of hydronium if you know the pH. So the concentration of hydronium is equal to 1.0 times 10 to the negative pH power. You just throw it up. Remember, pH is the power of hydrogen. There you go. That proves it. This first example is just showing you the variations on this Kw calculation. Notice that the concentration of hydronium, that's what it means to have those brackets around it, the concentration in molarity of hydronium multiplied by the concentration of hydroxide equals Kw. Well, we just derived Kw. That wasn't too hard. So that is your basic equation, and I've got it rewritten below. But how would you solve for the concentration of hydronium? Well, you can solve for the concentration of hydronium if you divide Kw by the concentration of hydroxide. If you know the concentration of hydroxide, you just divide Kw by it to get the concentration of hydronium. Well, what if you want to know the concentration of hydroxide? The last one there. Well, if you know the concentration of hydronium, then you divide Kw by the concentration of hydronium. So notice that no matter what, to find the unknown ion, to find the unknown concentration, whichever one you're looking for, you're always going to divide Kw by the one you know. It's Kw divided by the one you know gives you the one you don't know. So no matter what, you're going to be dividing Kw by the one you know. So now we're going to do an example using real numbers. And for this one, I've done a little bit of a switcheroo here. Notice that the one at the top says concentration of hydronium times concentration of hydroxide equals Kw. But the way I've written it just below that is a little different. It says the concentration of hydrogen ions times the concentration of hydroxide is equal to Kw. Well, it's up to you to realize that that means the same thing. Hydrogen ions are hydronium. Same thing. You've got to recognize that. It'll often be written either way. You just have to realize those are the same thing. So what if we know the concentration of hydrogen ions? What if we know that that is 1 times 10 to the minus 6 molarity, and we want to find the concentration of hydroxide? Well, those two multiplied together is equal to Kw. But what was Kw again? Remember we derived Kw? Oh yes, it was the concentration at pH 7. It was the concentration of a neutral solution of each one of them multiplied together, but they were the same number, 1 times 10 to the minus 7. So it was 1 times 10 to the minus 7 molarity squared. And then squaring molarity is kind of does weird things to the unit. It's kind of a disgusting unit. So we leave out the unit and we get 1 times 10 to the minus 14. That is Kw. We usually write it unitless because the unit would be too disgusting to even really look at and deal with. Okay, so now that we've got that, how would I solve for hydroxide? Well, remember, no matter what, you divide Kw by the one you know. So notice I'm dividing Kw, 1 times 10 to the minus 14, by the one I know, the hydrogen ion concentration, 1 times 10 to the minus 6. So why have I left out my unit here? Is that a mistake? Well, if I'm already leaving out the unit for Kw, what's the point of putting a unit below it? It's just not really going to help much. I just have to realize what unit my answer is going to come out in. Remember, no matter what, if you use a Kw calculation, the unit of your answer is always going to be molarity. Molarity, big M. So let's see. We can do this in our heads. 1 times 10 to the minus 14 divided by 1 times 10 to the minus 6. Well, 1 divided by 1 is 1. 10 to the minus 14 divided by 10 to the minus 6. Well, wait a second. So I'm dividing by, that would be subtracting, and I'm subtracting a negative 6. That's like adding 6. So it's like negative 14 plus 6. Okay, or I could switch it around and say 6 minus 14, and that'll be my exponent. It'll be 1 times 10 to the negative 8, and then I put back my unit because we do need a unit. It's molarity. All these concentrations will be in molarity, so don't be confused just because we leave it out for kW, and we sometimes might leave it out in the process of doing the calculation. The answer does need a unit. Molarity or moles per liter, of course, remember that's what molarity means. You could write moles per liter or capital M. Make sure it's a pointy M. So this is how you do any kW calculation. If you know one of them, you can solve for the other. And it doesn't have to be 1 times 10 to a power. It could be any number. And you would just get the right answer when you divide kW by whatever you have. It'll give you a pretty precise concentration of the unknown ion. For the next one, what we're going to use is one of the formulas for pH, but the question is a little bit tricky because notice what it's asking for. This is one of those things you have to watch out for on these pH calculations. It says, what is the hydroxide concentration when the pH is 4? So your knee-jerk reaction should be, oh, that's easy. It's pH 4, so the concentration would be 1 times 10 to the minus 4. But no. Notice it's asking for the hydroxide concentration. So we can get the hydrogen ion concentration from the pH immediately, and that is 1 times 10 to the minus 4 molarity. So we can insert that right there. But we still don't know the hydroxide concentration. For this, we have to use the kW calculation, the one on the bottom, the formula on the bottom. By the way, did you notice that I wrote them in the opposite order here? I wrote hydroxide first and hydrogen ion second, because order of operations, it doesn't really matter which one goes first. Okay, I just wanted to show you that. I did that deliberately. And what was kW again? We should know it by now. 1 times 10 to the negative 14. So that's kW. It's always kW for water. Okay, it's the equilibrium constant for water. And then how do we solve for hydroxide again? Oh, it's just like we did in the last one. You divide kW by the one you know. So now it's 1 times 10 to the minus 14 divided by 1 times 10 to the minus 4. I mean 1.0, I should say. So obviously 1.0 divided by 1.0 gives you 1. And 10 to the minus 14 times, divided by 10 to the minus 4. So again, it's like subtracting the exponents, and we're subtracting a negative, so it's like adding the 4, so it's like negative 14 plus 4, or 4 minus 14, and that gives you 1 times 10 to the negative 10. Oh, what's the unit? Molarity. I did not write that one in there, but that would be the answer. 1.0 times 10 to the minus 10 molarity would be the concentration of hydroxide when the pH is 4. But there's another way to do that. Okay, so pH is the negative logarithm of the concentration of hydrogen ions, right? So if I've got the concentration of hydrogen ions is equal to 1.0 times 10 to the minus 4 molarity. Okay, what's the negative logarithm of that? Oh yeah, take down the exponent, make it positive, 4.0. So if the pH is 4.0, how could I find, which is just like the last example, by the way, this is not a mistake, how could we find the hydroxide concentration more simply? Oh yeah, there's a pOH scale, isn't there? So if my pH is 4, what's my pOH? (10). So guess what? The concentration of hydroxide is going to be 1 times 10 to the negative pOH, or to the negative 10 molarity. So that is a much, much shorter way, notice, of finding that answer. If you know what the pH is, you also know what the pOH is. They go together. It's like 14 minus 1 gives you the other. So that means you can very, very quickly find the hydroxide concentration. Well, that's the case if it's 1.0 times 10 to any power. That'll work perfectly. What if it's not exactly on pH 4? What if it's like, I don't know, 4.5? Well, as you know, 4.5 is between 4 and 5. So I wouldn't expect you to be able to use that to give me the exact concentration. I would just want you to realize if it's greater than or less than what we had at pH 4. So here's the thing. Remember what I said about the most concentrated on the pH scale is when you get down towards 0, 0 and 1 are the most concentrated. And the higher numbers, the higher the number gets, the less concentrated. So think about a 4.5. That's between 4 and 5. 5 is a higher number on the pH scale, meaning it would be a lower concentration. So what I would expect you to be able to tell me is that the concentration of hydronium ions at pH 4.5 would be less than 1 times 10 to the minus 4 molarity. That's about as accurate as I would need you to be with this. Because otherwise, yes, logarithms can be tricky if it's not on like a whole pH. It can be a little tricky reversing that. And exponents with decimals are not a pretty sight, so we don't want to go down that route. Okay? But wait, what could I say about the hydroxide concentration? If the pH was 4.5 instead of 4, and then what would that do to the hydroxide concentration? Well, remember, they have an inverse relationship. So if the concentration of hydronium is less than 1 times 10 to the minus 4, well, guess what? Then the concentration of hydroxide would be greater than 1 times 10 to the minus 10 molarity. Why? Because it would be between 10 and 9, wouldn't it? If you take 14 minus 4.5, you'd get 9.5. So it's between 10 and 9. And of course, 9 has a higher concentration of hydroxide. So that part is definitely a little bit tricky. The last one I did there with the 4.5, that can be confusing. Just remember that pH is an upside down scale. The pOH scale can really help you out to find shortcuts. So now we've seen all three of these equations in action. We've seen the KW equation where you can find one from the other. We've seen the definition of the pH, and we've seen how to use the pH to find the concentration of hydronium. And then we've also seen how to use that using the pOH scale to find the concentration of hydroxide. So those are the quantitative parts of acid-base chemistry. And then there's just a few more things we're going to be doing that are quantitative, but this is the fundamental basis. So we'll get some practice with these, and eventually you'll be really good, and you'll find that some of these are definitely easier than addition.